voltage divider law. So voltage divider law, um, I am a big fan of it. I use it a lot in my homeworks and exams when I was an undergrad, and that's because that's the law that my professor favored. So voltage divider law, the way it's often taught in most schools is you have a circuit like this. You have some Vs, you have some R equivalent A, R equivalent B, and let's say you want to know the voltage of VB, and you want to know the voltage of VA. That's really close to my header. Alright, so the formula is such that VA is equal to Vs divided by R equivalent A plus R equivalent B times R equivalent A, and VB is equal to Vs divided by R equivalent A plus R equivalent B times R equivalent B. Now, I just want to make a small comment that if you drew a current, let's call it Ix, going clockwise, then Ix is Vs divided by R equivalent A plus R equivalent B. That's because if you simplify the above circuit, this is R equivalent A plus R equivalent B. That's Ix. This is Vs. So using Ohm's law, you can get this one. Ohm's law. Let us get to here, to the third equation. Okay, now why am I making a video on voltage divider law? I'm not just making a video to go over the equations, because I think your institute or your school's videos do a pretty good job at the formulas at the least. But I want to show you why. Well, first I want to show you two things. First, how to start visualizing when you do or don't want to use voltage divider law, and second, some tricks that I've personally have come across, developed, and or gathered from working with classmates and or other people who've taken this class. Okay, so an example. I'm whispering because I'm in my cubicle space, so I'm trying to whisper here. Alright, so example number one. Let's say you have a circuit like this. And they said, what is the voltage of V2? So let's say the question was, what is the voltage of V2? So first, if we're solving for V2, units of volts. Second, how would I go about this? Okay, well, look at the circuit, and some things I'm starting to notice. Notice what? R2 is in parallel to what? R3 plus R4. Therefore, VR2 is equal to the V what? Voltage of R3 plus R4. Which means I can simplify the resistance between this bottom node and this top node. So using simplification and our series, our parallel equivalence concepts, this is R2 in parallel to R3 plus R4. This is R1. And now what? If we're solving for V2, right? V2, all of this is equal to V2. So if we're solving for V2, now I could just use what law? Voltage divider law. Because I was able to simplify the circuit from here to here using these observations. So now V2 is none other than Vs divided by R1 plus R2 in parallel to R3 plus R4 times what? R2 in parallel to R3 plus R4. And why is this cool? Because if you did this problem on your own, you might have been told or you might have been guided to use node analysis. So I'm just going to write here. We solved this problem using VDL, voltage divider law, parenthesis after simplification, while someone would have used node analysis. Does that make the answer wrong? No. It just, in my personal opinion, this makes more sense for me, and for me it's more efficient. I don't like node analysis because node analysis, it's like Vx minus Vy over R plus or minus, and then the same thing, fractions and more fractions, and all of it equal to 0, and then I have to solve for Vx or Vy, and it's fractions, and it's just more algebra. And that gives me anxiety, personally speaking. So I don't like it. I have test anxiety. So instead, I had numerous homework problems in my undergrad days. So these observations, things that I notice, it's second nature. And perhaps for you, it may take some time, but you could go back to your homework problems and consider perhaps VDL is voltage divider law is something that you could have used if you had just simplified your circuit. In fact, I'm going to show you another problem that you could use voltage divider law for. Here is another problem. Okay, so we have this problem, and we are being asked, what is VThevenin? So we're being asked, what is VThevenin? And let's say we're doing units of volts. Okay, so how would you go about this? Again, there are many ways. The first thing that I do is I start writing my observations. I notice that VThevenin is going to be equal to VR4 because VThevenin is in parallel to VR4. So I'm just going to redraw my circuit so that for all my visual viewers here, what I'm seeing in my mind is this. Okay. Now, this is a little different than our previous example number 1. But now, in my mind, what I would love, I wish I had, is I wish I had something like this. Right? Because then I could solve for VThevenin. I could say VR4 is equal to VThevenin, which is equal to Vx divided by R3 plus R4 times R4. And it would be easy, done. Well, not easy. I shouldn't use that word. This is more direct. No mesh analysis, no node analysis, no nothing. Just VDL. But this leaves me with what? One equation and 2 unknowns. Because I don't know Vx. However, I notice that this circuit can be simplified to what? This is Vs. R1. And what's this resistor? It's R2. Let's redraw. It's R2 and parallel to what? R3 plus R4. And this voltage across this resistor is Vx. Right? For those who may be confused or need a little extra guidance, let me explain. Starting from the bottom, and my whole team here. I need to know the voltage across R2 because that's in parallel to the voltage from here to here, right? R2 is in parallel to the system of R3 in series to R4. So if I know the voltage across here, I can then replace that with Vx because the voltage across R2 is equal to the voltage across the network of R3 in series with R4. And I can set that just equal to Vx, which then allows me to have this circuit, which then makes me comfortable to use this voltage divider law. So from here, why don't we solve for Vx, which is equal to the voltage across the voltage of R2 in parallel to R3 plus R4, which is equal to what? Vs divided by R1 plus R2 in parallel to R3 plus R4 times R2 in parallel to R3 plus R4. Now I could put this equation back up here, which means at the end of the day, VR4, which is equal to VThevenin, is equal to, it's going to be craziness, but Vs divided by R1 plus R2 in parallel to the system of R3 and R4 in series. This is, times R2 parallel R3 in series to R4. This madness, what? Divided by R3 plus R4 times R4. This whole thing is equal to VR, which is equal to VThevenin. Now, one might argue that this was inefficient and they could have just come here and they could have done node analysis and put the ground here and put unknown voltage, usually called X, up here. Or they could have done mesh analysis and find current, I2, and then multiply that by R4, and that would give you VThevenin. Okay, to each their own. Everyone gets dressed differently. I choose my shoes because I love colors, and then I choose the outfit, the top and the bottom, my t-shirt and my jeans, or my chino pants. You might want to get dressed by choosing your top first, and then everything else comes after. I don't know. Maybe you don't care about matching. Maybe you do. Personal preference. I like voltage divider law because that's what I was kind of nurtured with and biased and exposed to repeatedly. I didn't have a lot of practice problems with mesh analysis or node analysis or current divider law. Voltage divider law was used almost every single class, so to each their own. But I'm just showing you it's possible to start seeing voltage divider law as a tool that you can really exploit. In fact, this problem was a Thevenin problem, and there's no one way to solve for Thevenin, but I'm going to show you a problem that was assigned to some students at some university or institute. They were told to use mesh analysis, node analysis. So now this is example number 3. And that example is, where are you? 1 second. Okay. R1, 4, S, yes. Question. What is V2? Originally, this problem was hinting to use node analysis, which I'm not a fan of because node analysis has fractions and I have test anxiety, so fractions may cause me to mess up my algebra, even though I'm a graduate student now and I was an undergrad back then. So I don't know. I don't like it. So I'm going to use voltage divider law. And some of you might be like, wait, how can I use voltage divider law? Because some of you are like, I don't see this drawing. R equivalent A, R equivalent B. You don't see it in this circuit. So perhaps you're not able to fill in the gap. Let me show you. How am I going to get this circuit shown on my left to this circuit on the right? Or to be very similar at the least. I'll show you. It's going to be fun. First, we're solving for V2. Not numerically, but algebraically. Second, I learned about source transformation. So I notice here, what is that? It's a Norton equivalent circuit, right? Sidebar. Norton equivalent circuit can look like this. It can also, it's the same circuit if it's like this. Because the current source and the resistor are in parallel. That's what has to be true. So it's okay if the current source is on the left side or it's on the right side. And thanks to source transformation, I can redraw either of them to what? A voltage source in series to a resistor. And that's the same thing as what? If I did it this way. Right? They're symmetrical, same thing, as long as you have a voltage source in series to a resistor. So, let's put in a Thevenin equivalent circuit, thanks to source transformation. So source transform R4 and IS into what? R4 and R4 times IS, which would be the V Thevenin, right? Because V Thevenin, let's say alpha, is equal to ISC alpha times R Thevenin alpha. This is ISC alpha, R Thevenin alpha, and that's the same for the right-hand circuit, and then for the left, this is just V Thevenin alpha, this is R Thevenin alpha. Okay, and they're the same variable names on the right-hand drawings. For the sake of time, I'm not doing it. Okay, so let's simplify the circuit. So now we have and again, what I'm doing takes time to comprehend. Actually, let me make one more comment. I messed up. First, we're going to group R3 and R4. Then we're going to take the Norton equivalent. So I'm going to say simplify R3 and R4. Then source transform R3 parallel to R4 and IS to what? To, it's still going to be R3 parallel to R4 and R3 parallel to R4 in parentheses times IS. Okay, so let's do that. So here, we've truncated, simplified R3 and R4, they're parallel to each other. We have R2, we have R1, we have VS, and then we're going to do the source transformation. So now we have So now we have R3 parallel to R4, and then we have R3 parallel to R4 times IS. This is R2. This is R1. Now, notice this is VS. Notice VS and R1. They're what? In parallel to each other. Therefore, VS is equal to VR1, which means I could simplify my circuit even further. Now I have this drawing. Why am I able to remove R1? I'm not claiming that R1's not there. I'm just saying that since they share the same voltage, another way to draw the circuit is here. Another way you could think about this is I'm looking at the outer loop. And what am I going to do here? I'm going to do a KVL. No, I'm not going to do a KVL. I want to simplify the circuit even further. Again, for those who are asking, wait, what about the resistor? Aren't you like messing with the currents? No, because if current is, so this is a node, right, that breaks. So the current that, I guess you could say, leaves the top node is the current that's going to flow through R2 and enter this node. So it started from the bottom, my whole team up here. So the current leaving at the top, going from left to right, let's call this I alpha. And let's call this one down here I beta. I'm saying I alpha is equal to I beta. I beta is going from right to left, it splits, and then the splits come back together. And so following KCL, Kirchhoff's current law, this current at the top has to be equal to I alpha. Let's call this I1. Let's call this I2. I beta, current going in, is equal to the currents going out, I1 plus I2. And at the top node, I1 and I2 are going in, I alpha is going out. I1 plus I2 is equal to I alpha. Therefore proving that I beta is equal to I alpha, which means I could draw this circuit. I alpha. And we already explained that this is I beta, and I alpha is equal to I beta. So let's just call this I alpha. Leave it at that. I'm going to leave the drawing just so if anyone wants to come back, they'll have it there. So I want to simplify this drawing even further. How can you do that? I have two voltage sources, but they are in series. Two voltage sources in series. So I'm going to put them, again, they're in series, they're human centipede. So the current, the food that all humans are going to have to swallow, unfortunately, is the same, right? The current that goes through R3 parallel to R4, take your pen and pencil, you can see I never picked up my pen, my stylus. So I alpha is going through everyone. So it's okay if you rearrange components, meaning let this be VS, let this be minus plus. This is R3 parallel to R4 in parentheses times IS. Minus plus E2, right? Because that hasn't changed. That at the very beginning, it was minus on the left. So I'm keeping that here. I'm just, like if this was your protoboard, I'm just moving R2 to a different location on the protoboard, but I have to keep the terminals the same, which would have to keep minus at the bottom, plus at the top. This is R2, this is R3 parallel to R4. Now what can I do with the batteries? The batteries, if you did the mountain journey, it'd be plus VS, and then when I get back to this voltage source, so it'd be plus VS minus, because if you went all around, it'd be plus Vs minus R3 parallel to R4 times Is. R3 parallel to R4 times Is. That's our new what? Our new big battery. So now we have this drawing. Again, let me draw this first. Hold on. So this is Vs minus parenthesis R3 parallel to R4 times Is. Okay, so if I lost anyone going from here to here, if I did KVL, it'd be plus Vs minus, let's call this I alpha, minus I alpha times R3 parallel to R4 minus I alpha times R2 minus what? R3 parallel to R4 Is. Let me zoom out. All is equal to 0 volts. Again, journey of mountains. Plus Vs, we're starting with Vs, we're going clockwise. Plus Vs minus I alpha times R3 parallel to R4 minus I alpha times R2 minus the battery that was shown here minus R3 parallel to R4 Is equal to 0 volts. I'll go one step back just in case. If I do the KVL for this circuit, it's also Vs minus I alpha R3 parallel to R4 minus R3 parallel to R4 times Is minus I alpha times R2 equal to 0 volts. Do you see how from this equation to this equation, all I'm doing is moving around terms, but not changing their positive or minus signs? Look at it closely, pause it, look at it, Vs, I alpha R3 parallel 4, I alpha R3 parallel 4, minus R3 parallel Is, minus R3 parallel Is, minus I alpha R2, minus I alpha R2, which is why it's legal for me to go from here to here, circuit up top to circuit in the middle on the left-hand side. It was okay for me to put the batteries next to each other, but I had to maintain the terminals and where they are. Now, going back here, I was able to go from here to here because what I'm trying to show you is I grouped the batteries. What allows me to do that? Algebra does. I'm just rearranging my terms. Plus Vs minus R3 parallel R4 in parentheses times Is. I'm just making that one big voltage minus I alpha parenthesis R3 parallel R4. That's this term. Minus R2 I alpha equal to 0 volts. So you see how this is one big term? That's what we have right here. Now we have, like I said in the very beginning, I'm going to make this circuit become this circuit. And I did. Look, right here. Using voltage divider law, V2 is equal to what? V2 is equal to Vs minus R3 parallel to R4 times Is, this whole voltage, divided by R3 parallel to R4 plus R2 times R2. This is comfortable for me, but that's because I can go from here using source transformation and simplification of resistors. I could go from there and understanding that Vs was parallel to R1 all the way to here. Again, I'm not saying you should be able to do this within minutes after watching a video that's 10 minutes and doing one homework problem in your life after learning about a brand new concept. But when you are in school, this is just a random example. When you're in a school and you're drilled to do problems like this, let me show you. let's say this is VS, this is R1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And your homework was, question, what is R equivalent in the circuit below so that circuit is same as drawing? And what R equivalent are we talking about? Talking about this. So make this circuit become this. Now imagine doing 7 or 8 of those problems like this. Oh, this has 13 resistors, sorry. Imagine doing that 2 or 3 times. Every homework. But like in the first week when we teach R series, R parallel, this would be your first homework. Now the following week, because we taught you voltage divider law, current divider law, I want to know the voltage across VR3. And then after that, I want you to use, let's say, I want you to use mesh analysis. This is I1, and technically, this is I2. Find the values of I1 and I2. And then after that, tell me the use node analysis to find the voltage, unknown node voltage at Vx. Crazy, right? And then, man, it could get even worse. I remember my professor, one professor, in another section, think I wasn't mine, was like, A, B, minus, plus, find V Thevenin. Find V Thevenin. Or find ISC. I'm not going to draw it, but if I drew a current from A to B, find ISC. And find R Thevenin too. Can you imagine? So, of course, truncating, it's something that I had to drill. So, I try to teach my students, if they want to challenge themselves, it's not required. I sometimes challenge them to see a circuit and consider viewing it from a different angle. Of course, this is, example number 3 is quite challenging to go from here to, from the circuit provided here to this circuit. But a circuit like this, maybe it's not as challenging. What we did was we took this circuit and we were able to bring it down to 2 different types. R1 and some R equivalent. It's called R equivalent. And we were able to also, this was VS. And then we were also able to do VX plus minus. R3, R4. That's a good job. If you're able to visualize this and conceptualize it, that's good. So don't beat yourself up. But I made this video because I just wanted to show how powerful voltage divider law is once you get the hang of simplifying circuits and or start using source transformation, R equivalent, R series, R parallel, etc. All right. Thank you for joining.